Okay, everyone, thank you very much for attending the last SNAPP seminar of the semester, and we'll have winter break and then start up again. So today it's my great pleasure to welcome Professor Laurent Massoulié, who is a researcher in Inria. He's been there for several years. He leads the Paris team in Inria. Before this talk, I decided to look up Laurent Massoulié. I mean, I've heard a lot about him. I've listened to several of his talks, but then it turns out there isn't a comprehensive bio of Laurent Massoulié available on the internet. So rather than ask him for his bio, I decided to give you the sentences that I know about him. I mean, I followed his work for several years now. Ever since I started my PhD, the stochastic block model was starting to get a lot of traction, and I was reading his papers back then. A couple of years ago, I heard him give a wonderful plenary talk on graph matching. He's done a lot of really cool work, not just on clustering, but broader machine learning models. So a lot of presence both in the stochastic system side as well as on the machine learning side. So we're very glad to have him here. And today he's going to tell us about his first forays into quantum, as he described it. So Laurent, the floor is yours.
Thank you, Ashwin, for the kind introduction. So what I'm going to tell you about today is based on joint work with Don Tausley and Janice Chen. Janice is a PhD student with Don, and she has done an internship with me about a year ago. And so this is the result of this internship and our collaboration since then. So title is Gaussian Boson sampling for planted bipartite clique detection. And my outline will be first what you need to know about the so-called Gaussian boson sampling, which is the quantum computing technique that we are going to be concerned with. Then about the planted clique detection or planted biclique detection, which is the hard graph problem that we are going to try and solve with Gaussian boson sampling. Well, we'll see. It's not a panacea for that. So the main result will be about the performance analysis we can make of a natural algorithm based on Gaussian boson sampling for addressing the planted clique detection problem. So I'll start off with introducing this GBS or Gaussian boson sampling framework. So this is a technique for doing computations with some quantum effects that has become popular over the last few years. One reason for that is that this is reasonably easy to engineer, to manufacture such devices, because you only need to have photonic circuits. So you don't need to cool qubits to extra low temperatures. It's much easier in terms of engineering to produce a device that does the manipulations that are needed. So here's a picture I took from one of the seminal papers on GBS on the internet. So you have a photonic circuit, you inject photons inside, and then you measure at output gates where photons leave the circuit. So there are a couple of variations on this. The basic version is with a single photon injection at the input gates. GBS itself, Gaussian boson sampling, is slightly different. You don't inject photons, you inject something else, but I will not say I understand what a squeezed state means, but this is what gets inserted. So the way it works is that you prepare the optical circuit for a task that you have in mind. Then you send the photons in and you measure where they live. And so we will now have a formal description of what we expect the device to do for graph problems. And this is one of the main applications that has been considered. So you use your photonic circuit to encode a graph with a set of vertices V and a set of edges E. and each of the output gates would correspond to one vertex of your graph. Then you choose a number of photons or squeezed states you will activate at the input. So that will be an integer m, which is going to be smaller than the number of vertices. And now what you measure at the output is a subset of m vertices. So this is a sampling device that samples subsets of vertices, and you parameterize the size of those subsets. So the formula gives you the probability of observing a particular subset A of m vertices, and it is proportional to the square of the Hafnian of an induced subgraph of your input graph. So let me walk through the steps. So the set A is a subset of vertices. G sub A is the subgraph that is induced by restricting the original graph to this subset A of vertices. And now the Hafnian of a particular graph is the number of perfect matchings of this graph. So this is a rather complicated sampling mechanism, but it depends quadratically on this particular graph matrix, this Hafnian of an induced subgraph. So a couple of comments on this Gaussian boson sampling mechanism. There has been a theory of what it means to be a universal quantum computer, and GBS does not provide you with a universal quantum computer. So this is a more restricted kind of device having quantum effects. Nevertheless, it is hard to compute Hafnians of graphs in general. So this is one of those counting problems, which is sharp P complete. The other famous sharp P complete problem is computing the permanent of a matrix. So the summation of a permutation sigma of the product over say the vertices I of I sigma I, so that would be the permanent of a matrix, and computing a Hafnian is at least as hard as computing permanence. So this is something that is not easy to do in polynomial time classically. So this is one of the reasons people think GBS might bring some quantum advantage. And maybe I should mention that this is one of several proposals that came out over the last few years of easy to engineer or to construct quantum mechanisms that may not be universal quantum computers, but that people are trying to assess whether they bring some advantage or not. Okay. So our question today is, does this device help solve some graph problems deemed classically hard? And as I indicated, the graph problem for us is going to be the detection or the reconstruction of a clique planted in a graph. So this is what I want to do now, describe you the planted clique detection or reconstruction setup. This is a very famous problem, and I guess several of you might know about it. So this works as follows. You start off with a random graph, G naught, on n vertices with some fixed probability of putting an edge between any two vertices, say P. Usually people consider P equal to 1/2, but you could take any fixed probability strictly between 0 and 1. And then from G naught, you form a second graph, G1, which is G naught plus a clique planted in G naught. So that is to say you pick a size K, that's the number of vertices in your planted clique. Then you pick uniformly at random, say, a subset of K vertices in your original graph, and then you fill in all the edges internal to this subset calligraphic K that you didn't have in the first place. So now this becomes a clique in your graph. So detection is the following task. You're shown a graph G, and this could be either G1 or G naught, but you don't know which, and you have to guess correctly. The second task that people consider usually is reconstruction. So now you are given G1, so a clique has been planted in what you get to observe. And the question for reconstruction is to identify exactly where the clique calligraphic K lies in your overall set of vertices. Both detection and reconstruction are known to be feasible in polytime. And this, perhaps the seminal work on that was a paper by Alon Sudakov and Krivelevich in 98. And they addressed it with spectral methods. So the method they describe in this paper is the following. You take your adjacency matrix, which has zeros and ones as entries. Then you subtract half to each of the entries. So now it becomes a matrix with entries plus half or minus half. Then you compute the eigenvector associated with the largest eigenvalue. And then you process this eigenvector. And the entries with the largest coordinate for the eigenvector, they will substantially overlap with the planted clique. So the procedure would be extract an eigenvector, sort the vertices by the magnitude, the absolute value of the corresponding coordinates. Then you restrict yourself to the top few coordinates, and then you have something that, when k is order square root n, will all overlap significantly with the planted clique. And then you can do some post-processing and strengthen this initial signal that is sufficient for you to retrieve the clique if it is there. And so you have various amplification techniques in this paper. So when k is, say, 4 square root n, you can go ahead with what I described. If k is a smaller constant times square root n, you need to apply the method to many embedded subgraphs, and then you have again a polytime method. But since you consider polynomially many graphs, then the polynomial complexity increases as you decrease the constant in front of square root n. So it's a weird kind of behavior. So we know spectral methods break down when k is small compared to square root n. And we know that many methods fail at both detection and reconstruction when k is small compared to square root n. For instance, one of the compelling results indicating hardness of this problem for k little of square root n was the works in 2016. So two simultaneous works almost showed that the sum of squares hierarchy of convex relaxations for this combinatorial problem will fail at any fixed level. And so the sum of squares hierarchy, so it's hierarchy of convex semi-definite programming problems. The first level would correspond to spectral methods, but as you increase along this hierarchy, the polynomial complexity gets higher and higher. And so at no fixed level of this hierarchy can you solve the problem. So this is a strong indication of hardness, and it's widely believed that with at least with classical devices, you won't be able to solve this problem with when k is little of root n. So there is a bipartite version of all this, which I'm describing now. So instead of having a regular Erdős-Rényi graph, you have a bipartite Erdős-Rényi graph. So you would have two sets of vertices, left vertices, right vertices, both of size n. Again, a probability p of putting an edge between any two vertices. And instead of planting a clique, you plant a biclique. What is a biclique? Well, that would be a collection of k vertices on the left, k vertices on the right, and then you would fill in all the edges between these two sets, adding a complete bipartite graph of size k on the left, k on the right to the original G note. So that would be the red edges on this picture. And so the story is very similar for biclique detection as it is for clique detection and reconstruction. So spectral methods say can do the job when k is omega of root n, but they fail when k is little of root n, and it is believed that no classical method will succeed when k is little of root n. Okay, so for us, biclique detection is a bit friendlier than clique detection when we want to talk about Gaussian boson sampling. This is why I bothered to introduce this. And so now what I want to discuss today is can GBS bring quantum advantage for planted biclique reconstruction? Okay, and as you will see shortly, as far as we can tell, it cannot. So this is the point we want to make in this work. So we will actually show results about a very specific use that we can make of a Gaussian boson sampling device. I'll call that the GBS node weights algorithm, and it would go as follows. So we fix a number of time steps, capital T, and for each little t, we sample a subset of vertices of our bipartite random graph, say with a planted clique, if we want to solve reconstruction. And so each of the subsets we sample has size twice m for some parameter m. And then because we are dealing with bipartite graphs and a subset that is reported by Gaussian boson sampling is chosen with probability proportional to the square of the Hafnian, then such subsets must have some perfect matching. And so because of the bipartite structure, then these subsets of size 2m for which there exists some perfect matching, these must be balanced between left nodes and right nodes. So set up this way, we would retrieve subsets with m vertices on the left, m vertices on the right. Okay, and so once we have done this sampling, then we would assign to each vertex I a weight W of I, which is the fraction of times we sample the subset that included I. Okay, so very natural approach. And then we would sort the items according to their weights. And the hope for this algorithm would be that just as when we take a spectral method and we sort the vertices by the entries of an eigenvector, then the top vertices comprise much more of planted clique vertices than a random subset would. So that's what works for spectral methods, and that's what might have worked for GBS, but as we will see, it does not. Okay, so and just to reiterate, so GBS favors dense subsets because the denser the subset, the larger the number of perfect matchings. And so the larger the Hafnian. And actually, in the original propositions of GBS, people said this is useful for identifying dense subsets in graphs. Well, so they reported experiments, but these were like experiments with 10 vertices. So it was not so compelling in terms of scale. Okay, and one thing to remark is that if we let the number of samples go to infinity, then the weight will converge to something that's proportional to the sum over subsets A of vertices of the fixed size twice m of the squared Hafnian of the induced subgraph GA. And so we will be very how to say, friendly with GBS, we will even assume that T is infinity. So we will not worry about finite sampling effects. We will just say, okay, we have access to weights thanks to GBS that are up to some normalization constant. This sum over subsets comprising vertex I of the squared Hafnian of the induced subgraph. Okay, and so here comes the result we could establish for this. So we assume that we have a parameter k which controls the size of the planted clique of size epsilon square root n. So the hard regime is when k is small compared to square root n. So that's when epsilon is small compared to 1. We assume as well that the parameter m that controls the size of the sample subset is also proportional to square root n, so it's alpha square root n. So the rationale for this is very different from the rationale for k being epsilon square root n. The reason for this is that when you do GBS, you may have, if you take m too large, multiple photons exiting from a single output gate. And if you take m of order square root n, that is the critical scale at which you start to see those multiple outputs multiple outputted photons for a given output gate. And this is, if you like the birthday paradox problem. So this is exactly that. If you throw m balls into n bins, you'll start to have bins with 2 balls when m is order square root n. So this is one of the constraints that people have imposed on GBS. Okay, so in this setup, we have a characterization first of the biases of the node weights. So that's what's written here. So suitably rescaled, the expected weight of a given vertex is some constant. So the exact constant does not matter. It's e to the p minus 1 minus 1 times 1 if this is a non-clique vertex. And if it is a clique vertex, it is 1 plus constant times epsilon over square root n. Okay, so we have a bias in favor of planted clique vertices, which is of a relative magnitude epsilon over square root n. The second result is about the fluctuations of those weights. So that's stated as follows. So if we pick a fixed collection of indices of vertices of left vertices, sorry, whether they be in a planted clique or not. Now we subtract to their weight wi the expectation, and we scale up by root n. Then these resulting random variables zi are asymptotically a Gaussian vector, and we can characterize the covariances of those limiting Gaussian random variables. So this is the formula at the bottom. So it's a constant times 1 I equals j for the covariance between zi and zj, plus a common constant alpha squared, where alpha was the parameter in the sampling number little m. Okay, so why is it bad news for GBS? If you take now k negligible compared to square root n, so that is to say if you take epsilon little o of 1, then the advantage in terms of biases for clique nodes over non-clique nodes is precisely order epsilon over square root n, so it's little o of square root 1 over square root n. On the other hand, the fluctuations of the weights, one with respect to another, they are, because of the result on the limiting Gaussian distribution, of order exactly 1 over square root n. So we see that the fluctuations dominate the bias, and so now if we come back to our basic way of exploiting sorted weights, we would want to take the largest weights, so the vertices with the largest weights. Say we pick a fraction 10%, c equals 1/10, and we extract the top n over 10 vertices, and we hope that within these n over 10 vertices, we have a fraction that is better. The fraction of clique vertices in this set, it's hopefully a better fraction than k over n, which is what we would get if we picked cn vertices uniformly at random without even observing the graph. But what this result says is that there will not be any difference. You won't see a boost in the fraction of planted clique vertices in the top weight vertices in this regime. So another way to try and make sense of this is one very basic way of trying to sort vertices and hopefully identify planted clique vertices is to look at the degrees of your nodes in a Erdős-Rényi graph with a planted clique. And so if you look at the degrees, these are binomial random variables plus some constant for the planted clique nodes. And so you have exactly the same behavior. You have some bias. The magnitude of the bias is dictated by the size of the planted clique. And then you have a Gaussian limiting behavior for the collection of centered degrees. And so it's no different. So at this level, it looks like using GBS is not more powerful than sorting nodes by their degrees. So which is okay. This is the sad news that we found for GBS. All right. So maybe before wrapping up, I just wanted to say a few words about how we prove those things. So the statements are short, but the proofs are long and painful. But I'll just give you a few hints about what we need to do in order to reach those conclusions.
Laurent, can I ask
Yeah.
a clarifying question?
Yes, sure.
And I should have said this at the beginning of the talk to the audience. Laurent said this is going to be a slightly shorter talk. So if you have clarification questions, please do chime in. So I missed something, and I'm just asking. So inherent to this claim you're making about the power of GBS is some sort of sufficiency claim that the W's encode all the information I could possibly have with Gaussian boson sampling. Is that? But is that
No.
true? Is that rigorous? I'm missing
No,
something.
this is a much weaker claim I'm making. I'm really making only a claim on a specific way that you could use GBS.
Okay.
So
So this is not a
extracting those
sufficiency claim.
weights.
Like in principle, maybe the collision statistics carry some information or something like that.
No, so we tried things like that. We tried to show that based on such weights. I mean I think a claim that would be strong that we don't make is that the distribution of the weights that you extract is in total variation close between the case with the planted clique and without the planted clique. So a statement about the distance in variation would be very strong. We do not have that, unfortunately. But it's interesting. So that there is one very nice result by Andrea Montanari and Ofer Zaitouni on the planted clique problem. So they consider actually instead of zeros and ones, they consider or of plus ones and minus ones. They consider the case where it's plus ones and minus ones plus some Gaussian noise, so noisier Gaussian, so perturbed Gaussian matrix. And so they managed to show that when you take the spectrum of the matrix, whether there's a planted clique or not, so the total variation distance between the spectra of the two matrices are close. So that's a very nice statement. We could not make such a statement, even though we were hoping at some point to make that, but at some well, it was so painful to get a weaker statement. Yes, we thought, well, we'll write this down.
Understood. Yeah. Sorry, this wasn't a criticism. This was just a question about whether there is a sufficiency claim. But yeah, I understand. Thank you.
Okay, so the way to show the Gaussian distribution in the limit is by computing moments. So we have an explicit formula for the moments of a Gaussian random vector. This is a Weeks formula. So this is expressed as a sum of perfect matchings over the coordinates of the products over the pairs in the perfect matching of the entries in the covariance matrix. So this is a complex formula, but it's actually an operational one to show Gaussian convergence. So what the thing we do is to take the moments, the joint moments of our variables of interest, and we try to prove that when n goes to infinity, we indeed have such a formula. And so if this holds for any moments, then we have a Gaussian limit. And so another thing we need to do, so to evaluate those joint moments, we re-express them as expectations of functions of random subsets of vertices on the left and random subsets of vertices on the right and random bijections between the vertices on the left and on the right. So this is a simple exercise to rewrite the joint moment of interest as an expectation over random subsets and random permutations. So this is how we capture these Hafnians, say. But then we need to do a probabilistic combinatorics in order to make sense of these expectations and to show that indeed the limiting joint moment is the one we are looking for. So maybe I don't need to go into those probabilistic combinatorics, but these are essentially a number of Poisson approximation results that we need in order to conclude. Okay, so that leads me to my conclusion slide. So yes, that's what I said. Our negative result is only about a very specific use of GBS. So we use those sorted node weights, and we say we cannot do much more or much better than with sorted node degrees, essentially. But this does not rule out the existence of smarter GBS based schemes. Although I would bet that they do not exist. So if I had to bet, this is what I would bet. And maybe I should mention, in Googling a bit yesterday, I came up with two papers, so put on the archive in September and November, which say that they can do classically the sampling that GBS pretends to be doing. But then, okay, this has to be checked carefully because there are a number of restrictions on the sampling they do, and I'm not sure this applies to the whole range of sizes of subsets M that one wants to consider. So maybe still this GBS does quantic things that you cannot do classically. But at least in some regimes of M parameter, you can do classically the sampling that GBS does. Okay, so if we want to have a practical consequence of this work, then we could say that we have found some evidence that planted clique reconstruction is something that is going to resist GBS. And so it turns out that there are many papers proposing cryptographic solutions where somehow the secret key would be a clique planted in a graph that is disclosed, that is the public key. And so an attacker using GBS would still have a hard time retrieving the private key from the public key in this setup. So, right. So that's what I wanted to say today. And so I'm happy to take questions if you have any.
Any questions from the audience? Please feel free to unmute yourself and ask directly. If you're feeling shy for whatever reason, you can put your question in the chat and then I can read it out. Maybe I'll start with just again a clarification question. This is the first time I'm seeing the sampling model, so I'm just a little. Maybe I just want to develop a little bit more intuition. Can you say a little bit more about? You said this thing about m being square root n because of birthday paradox, and that was kind of for physical reasons. But can you say, what is the range of m, and how does that actually affect what it is you expect to see in this problem? So, for instance, m small, m logarithmic, m polynomial, etc.
So people have come up with a formula for what you will observe that is more general than what I wrote down. So the general formula does not necessarily restrict to the case where you have one photon output, so either 0 or 1 photons coming out of each output gate, but you may have several at one gate. And so there's a formula with a Hafnian on the numerator, and then at the denominator, the factorial of the number of photons you see per output gate. And so this is what the physicists say GBS will do. But then, in order to analyze things, so even in the experimental papers, they restrict themselves to this range where m is order square root n. So going below with high probability, you don't see multiple photons at any output gate. The regime where m is order square root n, you see that with a probability that is strictly below between 0 and 1. So you could just filter out those experiments where you see several photons coming out of a single gate. So below that, definitely the sampling probability I wrote down corresponds to what physicists expect this device to produce. I don't know if I answered your question.
I have a follow-up, but let's maybe switch this to someone else who has a question. Vijay, your question.
Yeah, thanks, Ashwin. So just Laurent, thank you again. Just a question on the computational difficulty. Is it settled that a universal quantum computing device would solve the problem, or is that still open?
I think it is open. I think it is open. It's not clear that with a universal quantum computer you could do planted clique detection or reconstruction in the hard regime. But the reason why we thought this might be a good candidate was that the application people put forth was really identification of dense subgraphs. So it seemed like a natural match. But maybe a more powerful quantum computer would also fail at this task. It's quite possible.
Thank you.